Today I'll be talking about constructing confidence intervals for regression coefficients. Here you see the confidence interval equation, which has three parts. B and S sub B you've likely seen before in hypothesis testing, but as a refresher, remember that B is just the coefficient and S sub B is the standard error for that coefficient. These often have numerical subscripts which indicate which variable the coefficient and standard error are associated with. 0 indicates the intercept, 1 indicates the first variable, 2 the second, and so on. The coefficient and standard error will be given to you either with the regression output or just as part of the problem. The part that won't be given is this t-star. T-star is similar to a test statistic, like what you might have seen from hypothesis testing, but it's kind of the opposite. Instead of computing a test statistic to then get a p-value, we're going to use the confidence level to set the p-value and then work backwards to the standardized test statistic. So that star means that we're starting with a standardized p-value and working backwards. So, how do we actually find t-star? Well, first we need the confidence level. The typical confidence levels are 90%, 95%, and 99%, and the specific one will always be given in the problem context. Second, we determine the tail probability. To do this, we recognize that the confidence level is centered in the middle of our theoretical distribution. So to get the probability in each tail, we simply get whatever probability is remaining and split that equally between the two tails. Mathematically, that means that we're doing 1 minus the confidence, and then that result divided by 2. Third, we use the tail probability and the degrees of freedom to get the actual t-star value. Recall that anytime we're working with the t-distribution, the degrees of freedom are n minus k minus 1, where n is the total number of observations or data points, and k is the number of explanatory variables we have in our regression model. One important thing to note here is that Excel always expects the probability to the left of the value that we're looking for. So if we put in the left tail probability, Excel will give us the left t-star value. The left and the right values are the exact same numbers, but opposite signs. If we wanted the positive t-star value, we could input the probability to the left of the positive t-star value, which would be everything shown in red on the bottom distribution. So for example, if we used 0.025 for a 95% confidence interval in the t.dist function, we would get the negative t-star value. But if we used 0.975, the tail plus the middle probability, we would get the positive t-star value. We could also just get the negative t-star value and then multiply by -1 to make the positive t-star value. So why all this discussion on positive versus negative? Well, it's because of the role that t-star plays within the confidence interval equation. So let's take a look at that. Putting it all together, we'll have B and S sub B from either the problem or from the regression output. We'll also be given the confidence level, which will lead us to the tail probabilities, which then, in combination with the degrees of freedom, will give us the t-star value. With these three pieces, we can then do the simple confidence interval calculation, but a few cautions here. First, if possible, do all of your intermediate calculations in Excel. If you don't have regression output, go ahead and put the B and S sub B values into cells in Excel and make sure to label them. You'll also have to use Excel to get your t-star value. So once you have these three parts labeled, it's very easy to find the lower and upper confidence bounds. However, if you find and use the negative t-star value, what you'll end up doing is adding a negative value, which is basically subtraction, and subtracting a negative value, which is basically addition. So, in essence, if you decide to use your negative t-star value in this calculation, subtracting will give you the upper bound, and adding will give you the lower bound. That isn't intuitive, but it does make sense once we realize how we're adding and subtracting. But there's two easy fixes to this. First, you can decide to use the negative t-star value anyway, do both calculations, and then just figure out which one is larger, that's your upper bound, and which one is smaller, that's your lower bound. The other easy fix is to find the negative t-star value, but then just multiply it by a -1 in Excel so it becomes the positive value. Both of these methods work, and I find it easier to remember how to find and work with the negative t-star value than remembering how to find the positive t-star value outright. This is all to say, do whatever is easiest to remember for you. All of these methods will work provided that you input the correct values to the t.dist distribution. But some are easier to remember than others, and you won't have step-by-step instructions on an exam. So pick the way that makes the most sense to you and stick with it every time. That way, when a test rolls around, you won't get stuck. Once we find a confidence interval, there is the small matter of interpreting it. A lot of interpretation depends on the problem context, but I still wanted to give you an example so that you know how to formulate your own conclusions. Say that we ran a regression to determine if a drug that is supposed to reduce blood sugar levels is effective. We then found a confidence interval for the drug variable. How could we interpret that confidence interval? Well, we nearly always start off with the phrase, "we are 95% confident that," or a similar phrase. Then we describe the true value that we're interested in. So in this case, we were interested in the true average reduction in blood sugar. And finally, the third part is describing the bounds with the appropriate units. So we would say that's between 26.33 milligrams per deciliter and 32.86 milligrams per deciliter. The words in part 2 and the numbers and units in part 3 will vary depending on the problem context. And this isn't the only way to interpret a confidence interval, but I do find it a pretty standard interpretation, and since it only has 3 parts, it's not too hard to remember. Lastly, I wanted to touch on the importance of 0 being contained within a confidence interval. If 0 is contained within the interval, that means it's a possible value for the coefficient that we're interested in. That in turn means that there isn't necessarily a relationship between the explanatory and dependent variables that we were examining. This is a bit easier to understand with an example though, so let's go back to the blood sugar drug that we were just talking about. What if the confidence interval had been negative 5.06 to 7.05 milligrams per deciliter? That means that the drug could reduce blood sugar by up to 7.05 milligrams, or actually increase blood sugar by up to 5.06 milligrams. Remember that in this context, a positive value meant a reduction in blood sugar, so a negative value would mean an increase in blood sugar. But even if we were unsure what a positive versus negative value meant, we can clearly see that 0 is within that span. That means it's possible that the true effect of the drug is that it neither increases nor decreases blood sugar levels, and that is the important part. If 0 is within the interval, we can't definitively say that the drug has an effect on blood sugar levels. This is much like a hypothesis test result when we can't reject the null. It is still possible that the drug has an effect, but because 0 is in the interval, we can't rule out the possibility that it doesn't have an effect. And that lack of a relationship interpretation applies any time that we have 0 in the interval. So that's all I have to say about confidence intervals for regression coefficients. I hope this video helped you better understand how to find the t-star value and calculate and interpret confidence intervals. Thanks for watching.